So thank you for introduction us. So I'd like to talk about the scale modular kit. So we made a small black box type toolkit to explore the force-based interaction. Then here is a summary of our project. Summary video of our project. We made 3D force sensors packaging into the small black box. Then we can detect the touch position based on the force. Then in addition to that, we can capture the 3D position on top of it. This is the technical highlight. Later I will revisit it. Then we have 3 features: touch detection. Then this is object detection. Then in addition to that, we can also capture the human motions on a single platform. Then this is a summary of my project. Then here's the motivation of my work. The human activity, that's the common interest in the HCI field. So the human activity is everywhere. To augment the experience in a human life, that capturing or measuring or estimating the human activity is really important. Then to achieve the activity recognition, so we have a bunch of different type of sensors. Like from the vision-based module, the capacitive-based, the acoustic-based. Actually, I couldn't list up all the sensors, but we have many type of sensors. Then in this year, 2019, I'd love to revisit the force-based sensors for the activity recognition purpose. The reason is human activity can be characterized by force information. So we defined this kind of interaction as a force-based interaction, which the interaction is conveyed, the information is conveyed by the force vectors. So you can imagine our hand when you're drawing some letters. So that between the hand and the surface, there must be a 1 gram each, then 1 millimeter resolution force happens. Then when we put the object on your desk, there is a certain force based on the gravity of the Earth. Then in addition to that, so the more larger scale, between the body and the surface, we definitely have a force information. So my motivation is how we can capture all the information on the single platform. Then to capture the wide range of information, so researchers have been using these sensors. This is load cell. The load cell is a combination of the metal bar and the deformation gauge, deformation sensor. Then if you can replace the metal bar part, so that we can adaptively change the load maximum, the load tolerance, and the precision of the sensor itself. Then based on these sensors, the many researchers are working on the individual purposes. For example, the most recent one from 2016, the CHI conference. So the researchers working on the 3D touch detection on top of the load sensing. Then tabletop activity inference or the body tracking is another really traditional the target of the research of the load sensing method. Then we combined unified all the activity recognition purposes into the one platform. That's the part of our contribution. Then here's a list of our scale research. That we made a concept of the load-sensitive modulars, which is really adaptively versatile module for the force-based interaction. Then in addition to that, we had a big the technical invention that we made a 3D touch detection algorithm without prior information of shape geometry. Then we also made packaging this concept into the one small boxes. Then we made a GUI and modular hardware for the novice uses. Then also we conducted and we evaluated the system with having a workshop with 20 or more designers and corporate designers and engineers. Then here's a design space of a scale system. So I'd love to visit the one by one. For the first part, we made a toolkit, the scale toolkit. The most important part of our project is its modularity. So the users doesn't have to screw it to the modulars in every time. You can just place these small modulars beneath the surface or beneath the object. So you can put this basically everywhere, wherever you want. Then we combine from the modular sensors, we combine all the data into the total force. You can see the green line. That's the force vector. That's the most important the component of our research. Then this is a detail of our modular hardware and the architectures. So that we have a bunch of modulars. Then we connected it to the one microcontroller. That's a TNC base. That's an Arduino compatible microcontroller. Then we connected it to the host computer, and we had a bunch of modules like a touch detection, object detection, the motion detection. Then the users can easily make their own applications on OpenFrameworks platform. That's a C++ library for the interactive GUI making. Then for the right part, so that we made this the hardware. So that inside it, so instead of the traditional load cell with a 1D axis, just a Z axis, we utilize the XYZ, the 3D axis load cell. So this is a core point, the point of the technical point of our project. Then we classify the force-based interaction into the 3 categories. Then between the hand and the surface, that's a touch interaction. Between the object and the surface, that's the object detection. Then the body and the surface, that's the motion detection. Then from now on, I'd love to visit one by one. Then for the first, the touch detection. Then in the tabletop, the interactive surface community, the 2D touch detection is really a traditional field. So there's nothing new. We implemented that, but nothing we invented in the 2D things. However, we invented the 3D touch detection without the shape information. Then this is a video of our demonstration. Then when you touch the tripod, you can put the tripod on the 3 block modules. That's a scale toolkit. Then just touching onto the surface, you can get the rough shape information of the tripod. Then when you touch on the surface, you can easily make you can assign the virtual touch button onto any object without the prior shape information. Then I'd like to show the one step more the technical detail. So in the previous method, with the target geometry, if once you can capture these force vectors, you can easily calculate the intersection of the surface and the force vectors. However, without having a target geometry, how we can calculate the intersection? There's no surface information, geometry information. So there's a one-dimensional uncertainty. Then to solve that, we utilize the hand information. So we had a hand, but when we touching something, so we couldn't completely freeze. There's a slight unsteadiness is there when we touch the object. Then to utilizing this, the sampling the multiple force vectors, I guess you can see the intersection of all the green lines. So we estimate that the point as a 3D touch vectors. Then this works really well. Then this is a little bit mathematics about it. For the single force vectors, we can represent this equation of the line. Then when we capture a bunch of it, if you have n samples, we can make a matrix. Then what we can do is just solving it with a Sled matrix method. Then we introduce a generalized Tikhonov regularization instead of the standard Tikhonov regularization. If you are interested in some mathematics, you can visit in our paper. Then we implemented primitive applications on top of the platforms. For in the workspace, we can make the shelf really smart. We put the modules between the gray surface, then the red shelf and the inside contents. That's totally as it is. We didn't modify anything. So, but just putting the modules beneath the surface, we can capture the usage or statistics and how the user using the tools and the consumption of the tool components. For the post office, in the post office, there's a weight measurement. Then we can augment the measurement stage with the positioning sensor method on top of our scale modules. But in sacrifice of we get this 3D sensing capability in sacrifice of the slight delay. Then for the next, the object detection. Then object detection is demonstrated here. When you put the object on the surface, we can get the weight and its position. Then the system already know the weight of the object, so that we can keep tracking the location movement of the object on top of it. Actually, we cited the basement or foundation of our project is from the paper from the 2006. So there's a Lava Shack as a user interface. This is the title of the paper. So that they utilize the everyday object as a user interface. The concept is a weight as ID. So we introduced the weight as ID concept to our project, then combined with the weight-based identification, database manipulation. So we implemented object status tracking. Then here is an example application or a future scenario of our project. Then if we augment all the shelves and desks with the scale modules, so that's workspace already know the movement of the tools. Then if you lost your car key in your house, then the system already know that your key is a 100 gram, then that 100 gram object is in your kitchen. So like this. Then for the final functionality, so we implement the motion pattern detection. So we augmented the small square. That's you can imagine that's a part of the floor. So that system, that floor can sensitive of the 6 DOF vector. The 6 means 3, the upper part, that's the 3D axis, the force vectors. Then for the bottom part, that's the torque information, rotation information. So you can see so now I'm stretching along the y-axis, z-axis, then you can see these black lines. So that we can utilize this information to some recognition tasks. Then we implemented a really primitive, preliminary, the motion recognition pipeline on top of it. We extract the 6 DOF feature as a set of the standard deviations of the force and torque information. Then we classified it into the 4 different categories. Then this is a summary of the functionalities. Then to achieve the touch object motion information functionalities, we did samples over time. That's a key concept. The weight as ID. Then 60 motion vector. That's the technical features of my project. Then here's a one-page result of the technical evaluation. Then we conducted a technical evaluation. The horizontal accuracy, that's very nice currently. For the motion recognition, since we did a really simple one, using a support vector machine to classify the 4 things, so that we achieved a 90% thing. Then for the vertical accuracy, for the 3D touch detection, so currently it's a slightly rough, the 7 centimeter errors around the 50 centimeters height. So I'd love to improve these things for the future applications. Then we conducted a workshop to explore the application field of the load-sensitive modules. Thanks to the collaboration with the Panasonic Beta, the product company in California, so we conducted a workshop to explore the application space. That's the first purpose. For the second purpose, evaluation of the utility of our toolkit. Then we had a longer ideation session. Then we had in collaboration with the corporate designers, so that we made a bunch of ideas. Then we classified it into the 6 categories. So I guess that this is a really nice foundation of the force-based interaction. The key findings from this ideation that we really need touch detection systems. Then I guess our toolkit with a 3D detection technique could be contributing for this the force-based interaction method. Then we also have a hands-on prototyping session. Then after generating all the many ideas, we categorize the 20 engineers and the designers into the 4 groups. Then they individually, as a group, so they explore the application space on top of the Scale modular kit. Then one interesting thing is one group explore you can see the top right figure. Some group explore the floor-based ideas for the yoga lesson. Then the other groups can augment the stuffed animals or stuffed characters to make them interactive. Yep. Then this is comments from the workshop. Then this is the future challenges. Then I'd love to emphasize on the response things. So since we really convinced with the 3D detection technique, so we'd love to improve the speed of that project to the future. Then, yeah, this is a summary slide of our project. Now we are scaling up the project to the future. Thank you.
Thank you, Taka. Do we have some questions? Yes. Back row.
Very interesting.
Thank you.
I didn't the basic input devices. How many numbers do they give you? Because if it's 3 numbers, I don't see how you get 5 numbers out of it. So it's giving you more than one pressure number, right?
Yeah, right. Okay, thank you for the question. Actually, so the minimum requirement of our module is at least 3. So to support the one surface, we really need 3 points. Then we can accommodate 3 or more modules on top of it. Then after putting the multiple modules, we can combine all the information into the one total force lines.
Yes, a question right here.
Great talk. I might be misunderstanding, but is it possible for the system to estimate the shape of the object? For example, if you put the square on the table, not square, sorry, any kind of shape, and stroke the surface or just keep on touching, then is it possible for the system to tell, wow, this is a puppy or anything else? Yeah.
Yeah, thank you so much. So actually, the possibly that could be the future next project or next project. So now we are, really, passionately working on top of this project. So just touching on the object, so that we can roughly estimate the object shape. So maybe just swiping on this microphone. When we swiping on this microphone, so there's some reducted or reduced information of our the geometry and our human vectors. Then I'd like to. Make the shape information from that things. Yeah, that's a really challenging thing that I'm really passionate about it. Thank you.
Okay, we have time for one more very, 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 very quick one in the back there. Sorry.
Thanks for the great talk. Can you explain about the initial setup process? Like if you have those sensors, do you need to measure the distances or position those sensors, and then you're able to sense the touch and other interactions?
Sorry, say again. What's the point? Sorry, I missed the point.
I was wondering about the initial setup when you have those sensors and you have the environment.
Interesting. So actually, currently, we need to set the initial point of the module. So that we need to manually set the module 1, the relative positioning things. So for the next generation, so I'd love to put the relative position sensors between the things. So then the more easily deployable modules we can achieve.
Okay, thank you very much.